All right, PChem. I wrote out a few slides to help walk you through the second section of Chapter 3. Some of it gets pretty mathy, which is the reason that I wanted to do it this way, so that you can pause and maybe take notes or write a question down at your own pace. There's a couple of questions at the end that I am asking you to do, and I'll provide a key to those two questions on Sakai. I'm going to start Monday's class assuming that you've gotten through section 3.2, even if you haven't had the time to completely go through it. I think that it's sort of standalone enough that you could pick up what you need to pursue 3.3 in class. All right, so this section makes more formal some of the concepts that I introduced in class when we talked about heat and work. The first law of thermodynamics, I'd like to focus on the word law. When we use that in chemistry, remember that it's a series of experiments. And people have known for a long time that energy is this quantity which is often associated with chemical reactions, and it can be partitioned in different ways. We literally called the equipartition theorem in Chapter 2 a way of spreading out energy among different nodes. This more formalizes it to something as grand as talking about the entire universe. In equation form, the first law of thermodynamics basically says that the total energy of the universe is the sum of whatever you define as a system and everything else, which is almost kind of a self-determining equation. For us, in chemistry, we care more about changes, and that if something happens, whether it's a chemical reaction or some physical process, any change that happens in the universe is really going to give zero net change, but it might partition the energy from a system to the surroundings or the reverse. And that's why yet a different version of expressing the first law is this equation, which basically says any change that happens to the system is equal and opposite in magnitude to the change in the surroundings. So I said in chemistry, much more often than not, we are interested in changes in the internal energy of the system. Internal energy has the letter U, is a state function that only depends on the thermodynamic parameters of the state, such as the temperature, the pressure, the moles, etc. Now, systems may possess other forms of energy. For example, we use the letter E to represent the total, complete composite of all the forms of energy. Here, capital K means the kinetic energy, and V is the potential energy for the system as a whole. U is talking about the internal energy. Now, I want to be clear about this. We used, in our presentation in Chapter 2.9, the different manifestations of types of energy inside internal energy. And I'm sure you recall we mentioned translation, vibration, rotation, and electronic. I want to be clear that the translational energy in U is different than the letter K that I just represented here. The kinetic energy of motion represented by the capital letter K refers to the motion of the entire system as a whole. So imagine, for example, a balloon flying in the sky, rather than the collective translational energies that are encompassed by the 3/2 RT dot N term in U. So if you can think of the balloon, when we were talking about translational energies of individual particles inside the balloon, we weren't considering this balloon moving as a whole. That would be the capital letter K that you would be talking about. The internal energy, if defined as the system, is the internal energy inside the system. In most chemistry problems, we're going to consider the system to be so-called at rest, and so that kinetic and potential energy as a whole are going to be set equal to zero. For simplicity, people just use a shorthand, and you have to be careful of that. Internal energy is often just referred to as, quote, energy, and our concern is in the changes in this quantity. As we've stated, internal energy changes are exactly the same when comparing one state to another, regardless of the path that was taken. The first law can be stated in yet another way. Any changes in internal energy is equal to the heat plus the work. For infinitesimal changes, we throw in our little differential sign, and you'll notice that you see a differential sign in front of the Q and the W. Now those little hash marks on there from equation 3.7 will be important in a minute. But let's read my paragraph here and see if we can understand this. So these equations, meaning the one from the previous page and this one, tell us that heat transfer and the work done on or by the system gives us the change we are interested in. Notice that we're not using deltas in front of Q or W, because the use of that symbol is reserved for state functions that just compare the final and initial states. In more hardcore mathematics language, du is an exact differential, whereas the d hash q and the d hash w are inexact differentials, meaning that they're path dependent. I'll work you through this in more detail later in the video. So let's apply the first law from the previous slide to one of our systems. For this course, in Chem 321, we're normally treating work as the PV type. So we're talking about gases expanding or contracting. Now I know in lab Dr. Breen did a surface tension lab with you, and he might even use an electrochemistry experiment with you later in the semester. I'm not 100% sure. In those cases, work is part of the equations, but it's a different type of work, which I showed you when we started chapter 3. But just for us in class, in lecture class, let's do an irreversible expansion. So that expansion of a gas against some constant external pressure. So you might remember equation 3.2. The work is equal to the negative external pressure times the change in volume. So equation 3.6 becomes this. Now in an expansion, delta V is positive, which causes a decrease in internal energy. The system is losing energy by doing work. If the piston is not insulated, then the system will absorb heat energy to make up for this, and that would be isothermal. So the delta U for the work part would be negative, but if it's isothermal, the heat part will be positive, and this will end up being 0 for isothermal. Later in the semester in lab, you're going to do something called a bomb calorimeter. How does the first law apply to a bomb calorimeter? Now, bomb calorimeter is actually a constant volume and adiabatic calorimeter. So if you look inside my little black box in there, that's where the chemical reaction is happening. But the walls are not movable, so you're not going to be able to do expansion work or be contracted by the surroundings. So no work is done in that form. The heavy-walled stainless steel container is thermally isolated from the surroundings. Any heat released by the reaction, in this case a combustion, raises the temperature of the water filling the inner jacket. Technically not just with the water, but also the stainless steel and everything that's inside this big box. If you know the heat capacity of the entire apparatus, it's very straightforward to get the change in internal energy. There is no work component because it's a constant volume, so any measurement you do of any heat transfer is going to be exactly equal to the delta U. The subscript V reminds us that of these conditions, constant volume, which is a particular defined path. That's how you get around kind of the awkwardness of saying that what looks like a state function is equal to something that's not a state function. That's going to be true only for the path that we just defined. Here's the little math review that I stole from the end of the chapter, and I did a little bit of a remix and asking you to do some work as well. This is the part where you might want to go through line by line to make sure you're understanding what I'm saying. Please ask me any questions if you're unclear. So imagine you have a function that has two variables. So the function is z, and it's dependent on x and y. If there's an infinitesimal change in x with a constant y, The corresponding change in z is going to be a small change in z that's dependent on whatever that differential is with respect to x times the actual change. Another way of expressing this is this term that I just circled is the dependence of z on changes in x. Whatever that connection is, multiplied by the change that occurs, that's going to give you your change in z. Similarly, you're going to get a change in z if you know the relationship between y and z, and then multiply it by the change in y. Now, suppose changes in both of those variables occur. You're going to get what's called a total differential. So the change in z is going to be the component due to the x change and the y change. That's a total differential. Now, total differentials are said to be either exact or inexact. A differential is exact if this expression, called Euler's theorem, is true. In other words, the partial derivative of this differential with respect to y is equal to this partial, the partial of this expression with respect to x. So if those two partial derivatives are equal to each other, that's said to be an exact total differential. So here's an example. Here's a total differential. You've got a total differential in some function z. It's got some x dependence and y dependence. So I've set the first component equal to y squared plus 3x, and the second one is e to the x. Now let's apply the Euler test. The partial differential of the m part with respect to y is equal to 2y. The partial differential of the n part with respect to x gives me e to the x. This is not an exact total differential because it fails Euler's test. It seems to me, although the textbook doesn't say this exactly, is that there's no inherent connection between these two variables, x and y. They're just sort of on their own. And I think when we do a chemical example, this will become more clear. So here's an example that we know in the chemistry world as a function depending on pressure and temperature. So we're going to say the function v, or the variable v, which is a function in P and T, is going to be have an exact total differential. So the total differential of v takes us our dv by dp with constant t, and I did that separately. I got minus nRT over p squared. And then I took the derivative of v with respect to t. And that becomes my second differential. This is like the m and the n from the generic case. So the total differential looks like this. Now let's apply the test. Euler's test says that the first part, or the partial differential of m with respect to the variable t, which gives me this, is going to be equivalent to the n function partial differential with respect to p. And in that case, I got this value. Notice that this is exact. This is saying that the total differential of dv expressed in this way is an exact function. Now again, chemistry-wise, that should make some sense to you. These two variables do have their own relationship. And so it's going to make sense that as one moves, there's going to be a connection to the other one. And that's what leads to an exact differential. The significance of exact differentials is that if the total differential is exact, where the function has two variables, then the value of the integral of a total differential is simply the difference at the two limits of integration. However, if a total differential is inexact, you cannot take that integral. Unless the functional relationship between x and y is known, the integral cannot be carried out. Think about examples of Q and W, in which you don't know the value of each. I always give this example in Gen Chem. Imagine taking gasoline and just putting it in a big 55-gallon drum and just setting it on fire. Okay? That gasoline is going to explode and giving off a tremendous amount of heat energy. And there will also be some work because it's got to push against the atmosphere above it. But the majority of this energy is going to be given off in the form of heat. Now, do the same chemical reaction, but inside an internal combustion engine, in which you burn only a little bit of gasoline, and you engineer the piston so that a lot of the energy is given off in the form of work. Here, the difference between the magnitude of the work and the heat is going to be more close to each other. The magnitude is going to be close to each other. What this is saying is I've done a combustion of octane with two very different paths. There's no way to just do an integral for one of them and be able to do that integral without knowing what the path is. This is basically a real-life example of an inexact total differential. So here's a couple that I would like you to try. One is done in detail in the book, and then one you're kind of on your own. So for one that I'm telling you ahead of time works is try this chemical example. So use the van der Waals equation and set pressure as the function of the variables V and T. The total differential of the pressure is going to be the partial of the function with respect to V at constant T, dV, plus the partial of the function with respect to T, constant V, dt. So I rearranged the van der Waals equation for you to give you your function P with the two variables. Now turn this function that I just boxed into a total differential by calculating first the first term, that's like the M term in the generic example, and then the second one, that's your N term in the generic example. Then, once you get that, apply the Euler theorem to prove that dP is an exact differential. Finally, show that this one is an inexact differential using the definition. All right. I hope this made some sense to you. Please be prepared with any questions if it doesn't. Bye.